Good morning, everyone. So yesterday we did discuss about the batch design and the fed batch design. Do you have any questions with respect to that? No? Okay. So in today's session, we are going to discuss about the heat and mass transfer in a bioreactor, and we are also going to discuss about the scale up of bioreactors, because you always start small at lab scale, then you increase the volume, and then slowly you move it on to your large scale fermenter or the industrial scale fermenter. So we'll start our conversation today with mass transfer in bioreactors, but before that I wanted to set up the base with respect to some of the basics of heat and mass transfer. Okay? Now let's start with heat transfer. I'm hoping all of you have had courses in heat transfer. How many modes of heat transfer exist? There are 3 modes. So you have your conduction, convection, and radiation. Radiation is, do you think so? Oh, sorry. So do you think radiation would be applicable in bioreactors? Not to a greater extent. The most important would be the conductions and the convection. So conduction, we do have the equation, which is your Fick's law, where your K is your conductivity, the A is your cross sectional area, right? So this is your cross sectional area, and then you have your temperature gradient, dt by dx. In case of your convection, it is HA delta T, where your H is your convective heat transfer coefficient. The notation might change from textbook to textbook, but H is the most common notification that I have always seen. So H is your convective heat transfer coefficient. The area in case of convection is cross sectional or the surface. It's a surface area. And again, the temperature will be the temperature difference. Now, keeping these are the most basic, right? And after this, we get into the governing equation, where you have your in minus out plus generation is equal to accumulation, right? So the accumulation term for the is always given as dt by dx. Is it? Accumulation is with respect to time, right? So that's why when in a steady state scenario, you don't consider the accumulation, because there is no change in temperature with respect to time. In practical sense, do we use steady state scenarios or non-steady state scenarios, or unsteady state scenarios? It's mostly unsteady state, because the temperature is going to change with respect to time. Even in bioreactors, when you are going to work with the bioreactors, what are the source of heat in the bioreactor? The organisms are one source of heat, right? Because as they are multiplying, as they are going to grow, their metabolic engineering, metabolic mechanism is working, that is going to generate some amount of heat, right? So that is your generation that gets added in the governing equation, if you remember, for your heat transfer. What else is there with respect to your heat? What adds the heat? Mixing, right? The agitation, that will add a little bit of heat. Do you think the amount the amount of heat that is added through the biochemical process, that means the growth of the microorganism, or through agitation, is it very significant? The delta T, is that very significant in case of a bioreactor? It's not very significant. You're right. It's not very significant, but it still exists. Even a small variation in temperature can ruin your whole bioreaction. So it is very important to understand how the reaction is moving forward, how much of heat is generated from the biochemical process, that means from the cell growth, how much heat is being added through the agitation, and how much heat you are adding to the system. Heat from external sources is mostly used to maintain the temperature, the optimum temperature that is required for the cell growth or for the fermentation process, and it's also used for sterilization. So you can use the steam sterilization to clean your bioreactor at one point of time, right? So even that's one way of transferring the heat, but that is not when you have your material inside. You don't put the steam because otherwise you're going to kill all your microbes. So that's the basics of heat transfer. Sorry, before I move on to the mass transfer, which of the mode of heat transfer is prominent in a bioreactor, convection or conduction? Convection, right? So you'll be dealing with surface area. Majority of the times you will be dealing with surface area. You're going to see equations such as UA/dt, where your U is universal heat transfer coefficient, A is your surface area of the inside of your bioreactor, and the dt would be the temperature gradient. Similarly, you have mass transfer. So what are the different modes of mass transfer? Diffusion and have you heard of the term dispersion? Dispersion is when you have, I call it forced diffusion. And then you have your convection. So you have your diffusion, which is your D. D is the alphabet which is used to denote diffusivity. So dA dC by dx, but it's always like dA to B dC by dx, where your x is the distance that it has diffused, the dC is the change in the concentration or the concentration difference, A is your area, but generally when we are working with mass, we always work with flux. So when we say flux, it's per unit area, we go for that. So that's why you will see d dC by dx, because A would have gone on two sides of the flow to give you the flux. So in case of heat, let's say it's minus Ka dt by dx. Q by A, Q dot is your flux. Heat flow per unit area is going to be your flux. So mass flow per unit area is going to give you your flux. So when we are working with bioreactors, we are working with flux. The dispersion is given as E. Even that equation looks the same. So EA dC by dx or E dC by dx. This would be for your dispersion, this would be for your diffusion. The negative sign is going to say from higher concentration to the lower concentration. For the heat, the negative sign is from higher temperature to the lower temperature. The other is HMA dC or delta C, where your HM is your convective mass transfer coefficient. Now, for this H on your heat transfer side, that is a convective heat transfer coefficient, the HM, which is a convective mass transfer coefficient, if I do provide you that information, if I provide you with the HM value or the H value, you are okay to solve any type of scenario with respect to convection. If you are not provided with the H value, how do you estimate it? You use equations for Nusselt's number, right, which is a function of Reynolds number and Prandtl number. Same thing in mass transfer, Nusselt's number is called as Sherwood number, which is a function of Reynolds number and Schmidt number. This is the most important concept that you will be applying in heat and mass transfer in bioreactor. Your Reynolds number, the Reynolds number is given as U, which is your velocity, d, that will be the distance, right, rho, the density, divided by the viscosity, right. Now, u, the velocity of what? U is the velocity of what? Of the fluid, right. So, u is the velocity of the fluid. D is the distance at which you are trying to estimate your mass transfer or heat transfer. So, or the type of flow that you have, whether it is going to be, what sort of flows can Reynolds number tell you, whether it is laminar or turbulent, what sort of flow do you assume will be existing inside a bioreactor? You have your agitator moving, so you are going to have mostly turbulent. The regular standing fan that we keep in summer in front of our face, it's like churning air, right? It's basically generating turbulence, and it's trying to push that turbulence towards you. You have so that's why it's because it's a turbulent flow, you will feel air at one point of time, and then suddenly it goes away, and then again you feel a gust of air on your face. That's a turbulency because it's coming in bursts to you. The rho, the density is also very important. That's also of the fluid. The V is also of the fluid. So, fluid properties are important. The fluid properties are very, very important if you are trying to estimate your Reynolds number. Now, these Reynolds number are required to estimate your Sherwood number or your Nusselt's number, which are part of your heat and mass transfer respectively. Sherwood number is mass transfer, Nusselt's number is heat transfer. You have to have an understanding of the fluid properties. So, when we talk about the fluid properties, what are those properties? The viscosity, the density, you need to know all of those parameters before you go and start doing the calculations, right. So, estimating those is also an important parameter in terms of assessing the values for your heat and mass transfer. So, the other part is your Prandtl number and Schmidt number. Your Prandtl number depends on what? If you have the mic, if you can answer in that, that would be great. The Prandtl number would be dependent on is it for the fluid? Is it based on the geometry? Okay, do you remember a term called as alpha, which is your diffusivity? What is the equation for alpha? I'm so sorry for putting you at the spot, but do you remember? You have your K over rho Cp, so your density of the material, the Cp is your heat capacity of the material, K is your conductivity of the material. Does this alpha has to do anything with PR, the Prandtl number? You have your phone, you can check. What is the equation for Prandtl number? If I remember correctly, it's PRANDLT, Prandtl number.
V by rho. V by rho. That is kinematic.
Is kinematic viscosity by density? Where is alpha? Now where? In the numerator or denominator? What about Schmidt number? So your Prandtl number is kinematic viscosity divided by diffusivity, heat. Was it a Schmidt number? Okay, so what's the value for Schmidt number? See, I learned while teaching my students, undergrads there, that the best way, because you all are so inclined towards your own technology, to make you do the work that I am supposed to do, that is finding it. So give me the value of Schmidt number.
V by D है.
So V by D.
Kinematic viscosity by diffusivity.
Diffusivity, right? Is the density term there at all?
If you will convert it, is the density. Yes, if you will convert mu upon rho D.
Okay.
Kinematic viscosity will be converted to dynamic.
This mu upon rho D, right? So that's your Schmidt number. Now the rho, the D is the diffusivity, is the property of the fluid, of the material through which your mass, so whatever material, sorry. So if A is diffusing, right, it is diffusing through whether it is a fluid or any material, is a property of the material. right? We talk about the diffusivity of a membrane. So, it's a property of the material. So, the material property comes into picture when you are working with Schmidt number and Prandtl number. Reynolds number provides you the fluid properties. That's why these two are very, very important, and we are going to use them when we get into the heat and mass transfer, proper discussion about of the heat and mass transfer in the bioreactor. So, I hope this basic refresh of your heat and mass transfer concept are helpful later on. Okay, so mass transfer in bioreactors. So, mass is transferred under the influence of concentration gradient. Mass can only move from a higher concentration region to a lower concentration region. In case of a bioreactor, gas liquid mass transfer is extremely important, because in a bioreactor you are looking at mass transfer. Specifically, the one that you are mostly interested about is your oxygen, which you are sparging. So, when you are sparging air at the bottom of the bioreactor, it is going to throw bubbles in the bioreactor, in the medium, and the mass transfer, that means oxygen coming out from the gas molecule where it is in higher concentration into the medium where it is in lower concentration, and then to the cells. That transfer, this is a two-stage transfer. So, you have your gas bubbles. So, let us say these are your cells here. So, your oxygen is going to come out of the gas bubble into the medium, and then from the medium it is going to go to your cells. Now, if it is a small single cell, the mass transfer would be different. If it is a cluster of cells, the mass transfer is going to be different. So, the type of host that you use, the way they grow, or the way you are mixing it, how homogeneous your medium is inside, is going to determine how much of mass transfer of oxygen is going to take place. So, this oxygen coming out of the gas bubble, if you remember, there were two terms that we came across yesterday. One was OTR and OUR. OTR was oxygen transfer rate, right? And this was oxygen uptake. So, OTR is basically your this stage. OUR is this stage where the oxygen is being uptake by the cells to grow. Clear? Okay. So, in an anaerobic process, oxygen must first be transferred from gas bulk through a series, in an aerobic process, not anaerobic. Anaerobic process, you do not transfer any oxygen. You should have stopped me if I made a mistake. In an aerobic process, oxygen must first be transferred from gas bulk through a series of steps onto the surface of the cell. This is your step. So, you have sparged the oxygen. So, you have your reactor, you have your sparger, so it's giving out the bubbles here. As the bubbles are moving up in the medium, they are going to release their oxygen into the medium. The solubility of oxygen within broth is actually very, very poor. We did talk about that, because you are trying to dissolve oxygen in a liquid. That is where the concept of Henry's constant comes into picture. Now, temperature plays a very important role in determining how much of gas is dissolved within a liquid. The pressure also plays a very important role in determining how much of gas is dissolved in a liquid, correct? Now, let us have a very quick conversation about this Henry's constant. What would be the best example in your day-to-day life of Henry's constant? Soda can. You have carbon dioxide dissolved in the soda, or like in the liquid, right? So when you open it, you hear that noise, right? So that's like it's under pressure. Within that pressure, the carbon dioxide is dissolved. But the moment you open, you will see that fizzy bubbles coming up. So that means that your carbon dioxide is coming up. The other would be, we call it diverse bend. So if you do a deep sea diving, you go pretty quick inside. The pressure of the water is pretty high on you. The nitrogen gets dissolved in your blood. And if you come up very, very quickly, that nitrogen, the pressure has been released on the body, that nitrogen will become a bubble and will stop the blood flow. It can kill you. Okay, so this is what happens. The other part would be when you are moving from, let's say from NIT Rourkela, you are going all the way to Himalayas. When you go up the mountain, you feel that oxygen is less in the air. Is it that the concentration of oxygen in the air is also itself less, or less oxygen is dissolving in your blood? It's less oxygen which is dissolving in the blood. Will the concentration of oxygen change from ground surface onto the mountain top, or the air will have constant concentration of oxygen throughout? That's the question that I ask my undergraduate students every time. It's a homework, think about it. It's a pretty good, it's an interesting topic. So it's basically the amount of oxygen that is dissolving in your blood is less when you go on a higher altitude because of the pressure difference. So enhancement of gas liquid mass transfer during aerobic fermentation is priority. If you're working on aerobic fermentation, because oxygen is required for your cells to grow and to flourish, you have to make sure that you are able to transfer the oxygen in appropriate amount that is required by the microorganisms for their growth. If you're not able to provide that, you're going to see cell death. Okay, so you're going to see cell death if there is, the oxygen is not about, sorry. So whenever the light goes off, it breaks the continuity of the thought. Oxygen transfer is very, very important in a bio process. You have to make sure that you are providing appropriate amount of oxygen. So that means the OUR cannot be less than OTR. Can it be? Oh, sorry, OUR cannot be more than OTR. So oxygen uptake rate is higher, OTR is less, you won't have any oxygen for the uptake anymore, right? It's the other way around. I will say things which will be other way around just to check whether you are listening to me or not. And if you're not saying yes, that means you are just agreeing to everything I am saying. Think, use your brain, okay? Now, mode of mass transfer which is common in a bioreactor is molecular diffusion. So, movement of molecules under the influence of concentration gradient is what is used for with respect to the diffusion. Now, continuous diffusion, that means supplying material to the high concentration region and removing it from the low concentration region is possible, right? So, if you continuously provide the, if you maintain that concentration gradient, you can maintain continuous diffusion process. So, if you maintain that OTR at a very high level, your OUR will remain. If you don't have that OTR, you cannot have your OUR. You won't have any oxygen for to be taken by the microbes. Now, continuous diffusion is exploited for mass transfer operations in bioreactor. The fixed law of diffusion, which we already discussed, is basically used in terms of estimating the amount of mass that has been transferred. So, you do need to know the diffusivity, the concentration gradient and the distance through which it is diffusing through. Now, mixing, as we have already discussed in the very first slide when we were having a conversation about the mass transfer, is a very, very important unit operation, you can say, in a bioreactor. So, mixing, that means turbulence in fluids produce bulk mixing to a max. up to the smallest eddies formation. So when you are having your agitation taking place, you are going to have small eddies which will get generated. You know what the eddies are? It is like a vortex, right? They are very small vortexes which will form, and those vortexes allow a very nice mixing ground. It's like, have you ever seen a movie called Twister? No? If you get a chance, there is a new movie called Twister. Watch it. It's really interesting. Or have you seen a tornado on TV? It's moving very, very fast. So it's actually mixing everything. Just think about that at a very microscopic scale taking place inside the bioreactor. In an eddy, if you are in that particular eddy, what is going to happen? Your mixing is pretty quick. So oxygen and the cell, if you have the gas bubble up there and you have the cell also up there, the oxygen transfer would be faster. So within the small eddies, flow is largely streamlined so that the further mixing must occur for diffusion of fluid components. Mixing on a molecular scale therefore completely relies on diffusion as the final step in the mixing process. Yes, eddies are there, but diffusion is the main parameter through which the mass is transferred. Now, mass transfer between phases occurs often in bioprocess. So, in the case of your gas bubble moving through, let's say, a liquid media, if I give you a column and I'm sparging oxygen from the bottom, let's say, so the bubbles will move up, right? And this particular column is filled with water. So, the bubble is going to move up from bottom, it is going to move up. What will happen to the size of the bubble? Will it increase, decrease? If decrease, why? If increase, why? If you have a fish tank at home or an aquarium, close your eyes, remember how the bubble is moving up in the aquarium. It remains in the same size, or it increases in size or decreases in size? It increases in size as it goes up, right? Why? Because of pressure? Keeps on decreasing, right, for the depth. And by the moment it has touched up, it has become bigger. Now, oxygen transfer from gas bubbles to the fermentation broth will also follow the same principle. That's why when you are sparging oxygen, the design of the sparger plays a very, very important role. You don't want smaller or bigger bubbles, like you don't want bigger bubbles to go through the medium. You want very small bubbles, because very small bubbles can be uniformly distributed and homogeneously mixed. So, you have to make sure that when it is moving up, it is in a very small shape, like the size of the bubbles is very, very small. So, the design of the sparger itself is a very important parameter in the design of a bioreactor. The other part would be, what are the restrictions, what are the phases that the oxygen has to go through. So, oxygen inside the bubble is in the gas phase. Now, when you have a bubble, it is inside a liquid media, you have a film that generates at the surface, right? So, the oxygen has to come out from the gas bubble, go through this particular film into the, and this film is because of the liquid media, surface tension, right? The bubble is going through the liquid medium, so it's going to have a sort of like a restrictive film across it, which will get generated, and that particular film has to be crossed before the oxygen goes into the medium. So, it's a very important parameter to look at. Similar type of film does exist on the cell structure itself. So, you have now two films through which the oxygen has to go through. The movement of oxygen in a bioreactor is also called as a two-film theory, because of these two films that exist. We will be discussing that in detail, but I am just giving you a bit of a basic idea to it. So, oxygen transfer from gas bubbles to the fermentation broth takes place, goes through the two phases. So, it is going from the gas bubbles to the fermentation broth. Now, product recovery from the aqueous to organic liquid, the nutrient transfer from liquid medium into the cell is also going through phases, right? There are two phases, from liquid to the solid. The cell is considered as a solid medium, not as a liquid medium. The fluid velocity near the phase interface is significantly decreased. Diffusion becomes crucial for mass transfer across the phase interface. Why? Here comes the concept of convection. So, let us say if I am going back to convection for a moment, if you have a flat plate, now I am going to talk about convection from the heat transfer perspective first, then we will talk about the mass transfer perspective. So, you have a flat plate, the air is going to flow over the surface of this flat plate. It is going to flow in layers, right? That will lead to formation of a velocity boundary layer, right, and a thermal boundary layer, depending upon which particular, whether the plate or the fluid has a higher temperature. So, the thermal boundary layer will exist and a velocity boundary layer will exist. Now, what is this boundary layer? If you remember correctly, it used to be the 99.9% of the distance at which the fluid will have the same temperature as the surrounding fluid or the. So, if this is at higher temperature, let us say 100 degrees Celsius, this one is at 20 degrees Celsius. What is the temperature at the surface? The plate is at 100 degrees Celsius. The fluid which is moving over the surface of the plate is at 20 degrees Celsius. What is the temperature at the surface? $100, 20, 60, 50, 40, 80. What is the temperature at the surface? I have given you so many options now. We call it the film temperature. At the surface, the velocity of the layer of the air at the surface is 0. What is the mode of heat transfer at the surface of that layer with the surface of the or the heated surface? What is the mode of heat transfer then? Conduction. Same concept in convection. The fluid is flowing over the surface. At the surface, the velocity of the fluid is 0. What would be the mode of convection then? What would be the mode of mass transfer? Diffusion. As the bubble is moving up, it's moving up. At the surface, there is that layer through which the diffusion is going to take place. The mode of is convective mass transfer, but it has diffusion at the interface. The transfer is called convective mass transfer. It has diffusion at the interface. Just the way you have conduction at the interface. Now, to answer that question, what would be the temperature? Is the film temperature. The film temperature is an average of your surface temperature and the fluid temperature. So, that means 60. So, from 60 degrees Celsius, you are going to reach all the way to 20 degrees Celsius. So, with the distance at which the fluid temperature at the surface, which is 60, it will keep on lowering down and it will reach the fluid temperature of 20 degrees Celsius. That distance is called your thermal boundary layer. If the velocity of the fluid is at 1 meter per second, at the surface it is 0 meter per second. The distance at which the fluid layer goes back to 1 meter per second is your velocity boundary layer. Same concept is followed in mass transfer. At the surface, it's always a surface phenomena. It's the most interesting thing. Generally, you have studied this concept of boundary conditions. Have you studied boundary conditions? So, let us say I give you a membrane or like a thick slab of membrane. You have diffusion taking place, right. So, it is minus d dc by dx inside. At the surface, you have air blowing. So, here you will have HMA dc, right, or delta c. The flux remains the same, mass conservation. So, your minus d dc by dx is equal to HA delta c or HMA delta c. At the surface, what is the boundary condition? At x is equal to 0, minus d dc by dx is equal to HMA delta c. That is what your boundary condition is. So, now coming back into your bioreactor with the same concept, what would be the boundary condition at the surface of the gas bubble? It is diffusion, and if it is moving with a velocity, it would be convection. You are getting my point? If it is stationary, diffusion only. With the flux has to be conserved, mass has to be conserved, right? The mass flux has to be conserved. Now, the theories of interface mass transfer. There is a two film theory and a penetration theory. In the two film theory, the entire resistance to transfer is contained in two fictitious films on either side of the interface, in which transfer occurs by molecular diffusion. We will look at what that film theory looks like later on. So, the KL, which is your diffusivity constant or parameter, would be given by d by z, where d is the diffusivity and the z is the film thickness. The mass transfer coefficient is the KL. You would see there is a term called as KLA, which is used in estimating your oxygen uptake in a bioreactor. The A is your area, d is your diffusivity, the z is the distance that it has moved, it requires for the diffusion. That combined gives you the KL, and the A gives you the area. The penetration theory, on the other hand, assumes turbulent eddies travel from the bulk of the phase to the interface, where they remain for a constant exposure time t. The solute is assumed to penetrate into the eddy during its stay at the interface by diffusion. So, the KL for that particular case is given by this equation. Do not get bothered by the equations that much, but understand the conceptual part. At the interface, what is your boundary condition? That matters the most. If there is a thick layer at the interface, the diffusion of the gas has to come from inside, which is at highest concentration. It is going to diffuse through that thick layer and into the medium, and then from the medium it is going to go into the cells. That thick layer will have its own resistance, similar to resistances that you see in your mass transfer. You remember, right? Minus dA dc by dx, the resistance is given by dc dx by minus dA, L over dA. This is your resistance. R diffusion, resistance to diffusion. Remember this? We also use a term called as K, which is your distribution coefficient when we are working with mass transfer, which has to be multiplied to your diffusivity for a specific product or a specific component which is diffusing through the membrane or anything like that. This is mostly used when we are working with the membrane. Now, the film theory, so this is your phase boundary. You have your gas phase and then you have your liquid phase. So, the gas phase film resistance and then you have your liquid phase film resistance. So, the rate of mass transfer is directly proportional to the driving force for transfer, which would be the concentration gradient, because that is the only driving force. If the concentration gradient does not exist, mass does not move. And the available area for the transfer process to take place. Transfer rate is directly proportional to transfer area. The transfer rate is also directly proportional to the driving force. So, driving force is the concentration gradient and the A, the area. This K is your proportionality coefficient. In case of heat transfer, we generally use the K as conductivity, but in this case we are not going to use it as conductivity, we are going to call it as the mass transfer coefficient. I have used the same as HM before, but I said it is convective mass transfer coefficient, but here we are using it as a K because the diffusive values it. The K is already estimating d by z, right? So, it already has the parameter of diffusivity in it. So, I am not representing it as d, I am representing it as K. This is because of the film theory. The K depends on the boundary layer, the geometry, the flow and the fluid properties. Why? Reynolds number, Schmidt number are involved, right. So, Reynolds number is going to give you the require all the fluid properties. If the material is very viscous, what would be the mass transfer? Will it be less? Will it be more? It would be less, diffusion would be less, right. If it is viscosity is the most important fluid property. Other would be the speed at which the fluid is flowing, that will determine the rate of mass transfer, the value of K. What else can be taken into account? The temperature, the density will define, not the temperature, the density will define. Change in temperature will change the density, but density is the parameter that will define. So, density, viscosity, right, all of these will come into the fluid properties that we are looking at. So, the gas liquid mass transfer, the rate of mass transfer of a component A through the gas boundary layer, that means your gas boundary layer, is KGA CAG minus CAGI. So, at this layer, the distance, the concentration gradient. Similarly, for the liquid side, it would be KL CALI minus CAL. So, the thing is, there is always a resistance at the boundary, at the phase, right. So, when you have your concentration coming in, it is at a lower concentration at the surface than the concentration that was there in the bulk. Then from there, when it goes into another phase, there is a drop. Let us say if I use a membrane, there will be a drop in the concentration within the membrane if the concentration on the left hand side of the material is pretty high than on the right hand side. So, there is a drop, because that would be determined by the diffusivity parameter or permeability of that membrane, how much of the material can be diffused through at a given time. If it can only give, let us say if 10 molecule comes on the one side of the membrane. So, if this is the membrane, 10 molecules have come from the bulk and they are like, hey, I need to go through, but this particular membrane can only allow 2 at a time or 3 at a time. It will only allow 3. So, there would be a dip in the concentration from the surface within it. At this surface, you will have 3. Now, this 3 is still higher than what is present on the right hand side. So, that dip is what you are seeing here. Got the concept? In the most layman way I am trying to explain. There is a dip because of how much can go through at a given time. That's the resistance of the film that will determine. Now assume equilibrium exists at the interfaces CAGI and CLI can be related. Equilibrium concentration in the gas phase is a linear function of the liquid concentration. The steady state at interface, there is no accumulation of component A. So, there is the K star distribution coefficient is not existing there. The component A transported through phase 1 must be transported through phase 2. These are the assumptions that you have to make. So, your NAG is equal to NAL is equal to NA, the total flux. The mass is conserved, or the flux is conserved at all times. Now, oxygen mass transfer. So, when you multiply equation 2 by m, so your equation 2 is here on the liquid side. And rearrange, you get this particular equation here. Now, dividing the equation by m will provide you further. So, the overall, the most important equation that you have to look into would be this, or sorry, this, where the KL is the overall mass transfer coefficient. So, KL is CAL star minus CAL. This is the equation that determines the mass transfer. You have your flux is equal, sorry, you have your mass flow on one side, you have your KL, which is the overall mass transfer coefficient A, and the CAL star minus CAL. Where exactly will you have the CAL star? At the interface. Now, this particular concept that is there. So, liquid phase mass transfer resistance dominates and the KGA is much larger than the KLA. So, liquid side mass transfer resistance is more as compared to the gas side resistance, which is an obvious thing. Liquid side will have a higher resistance as compared to the gas side. So, the KGA would be higher in terms of to maintain the flow. So, the rate of oxygen transfer from gas to liquid is of prime importance in an aerobic fermentation process, because without oxygen the microbes are not going to grow. But understanding how much oxygen is required, the oxygen demand of the microbes will provide you with the information which will make you capable to estimate the flow rate that you will set up, so that your oxygen transfer rate is always higher than the oxygen uptake rate. Can you, so let us say if I give you a bioreactor, you are purging oxygen into it, I ask you to stop it, what will happen? What is the worst case that will happen? Eventually the cells will die, right? But what if you reduce it only for a certain period of time and then again increase it? Will that impact the metabolic pathway of the cells, or what type of product is being formed by the cells? Because for survival, the cells will change their machinery immediately, and then again when they get it, they are going to go into a different mode. So, that switching of the mode takes a bit of time. So, there is always some products which gets generated during that period. So, it's always you have to always make sure for an aerobic fermentation system, you are maintaining the oxygen demand that is required by the fermentation system. Otherwise, the product that you are expecting, the quality of the product that you are expecting might not be there. At high cell densities, oxygen is quickly consumed in an aerobic culture and must be constantly replaced by sparging. The low solubility of oxygen, which is max of 7 to 8 ppm at ambient condition. Now, if you ask me what an ambient condition would be, I will say 25 degrees Celsius. That is what an ambient condition is for us. What would be the ambient condition in a bioreactor? (25 degrees Celsius). The ambient condition is ambient condition, you do not change it. So, the low solubility of oxygen limits the concentration difference, the CAL star by minus CAL, to very small value at all times. What it means is, like, once the oxygen has come out of the bubble, so now once the oxygen has come out of the gas bubble, it has to be in the liquid medium. But if it does not dissolve, if it does not solubilize in the liquid medium, it cannot be transported. Now, if the solubility is less, the concentration in the liquid medium available of concentration of oxygen in the liquid medium is less as compared to that present in the gas that might be available for the cells to obtain. So, that means your oxygen concentration in the liquid medium is lower, that is an obvious thing, as compared to what is there in the gas. But because of lower solubility, it goes even lower than what is present. Like, you have added, let us say 10, but only 5 or 6 would be available for the cells because the solubility is less. Now, solubility is depends on the temperature, solubility depends on the pressure, solubility depends on the fluid properties. So, all of those parameters has to be taken into account when you are trying to define how much oxygen would get solubilized. What can you do in that case? If you want to improve the solubility of your fermentation system, what will you do? You can change the type of medium that you are using that might be able to dissolve more oxygen in it, or you can provide some sort of let us say additives that will help dissolve oxygen, but all of that will impact your fermentation process. So, you have to be very careful in choosing what you can do to maintain this oxygen demand. So, designing of the fermenters for aerobic operation takes these factors into account to provide optimum mass transfer conditions. Now, factors affecting cellular oxygen demand. Now, the rate of oxygen consumptions by cell determines the rate of oxygen from transfer from the gas to broth. The OTR is dependent on OUR, how much oxygen is being taken away, that will determine what the OTR would be. That means oxygen coming from the gas bubbles into the liquid medium. Now, factors that influence this oxygen demand are the type of microbes, the host, the type of microbe that you have chosen for the fermentation process, the species. Some microbes require higher oxygen, they have a higher oxygen demand, some do not have that high as compared to the others. The culture growth phase, whether it is in the lag phase, whether it is in the log phase, early log phase or later log phase, like in the deacceleration stage or in the stationary phase, the oxygen demand will change. Will it not? When do you think, in the case of the cell growth, the oxygen demand is the highest? The early growth phase to the exponential phase, as it is being the constant phase where you have the constant growth going up. Your oxygen demand is high. You need, as it is doubling, right? At this particular stage, when it is trying to acclimatize, you might not have a very high oxygen demand. But the moment it will start dividing, the oxygen demand will shoot up. And you have to make sure during that period, you're providing appropriate amount of oxygen into your bioreactor. And the nature of the carbon source in the medium. The type of source of carbon that you choose will also define how much oxygen is there, is available. Because if the source itself interacts with the oxygen, then less oxygen is available. Okay? So you have to be very cautious about the choice of your source. Now, factors affecting cellular oxygen demand. So, in a batch culture, the rate of oxygen uptake varies as the concentration of cells increases during the cultivation period. This means that the rate of oxygen uptake is proportional to the number of cells present. So, as the number of cells will increase, the rate of uptake of oxygen will increase. So, in a batch culture, the rate of oxygen uptake varies as the concentration of cells increases during the cultivation period. So, as you are growing, the bulk of the cell mass keeps on increasing, your oxygen demand will also keep on increasing. Now, the specific oxygen uptake, which is your QO2, or the specific oxygen uptake rate increases to a maximum value at early log phase, and then it decreases gradually. At early log phase, it will start, it increases and then it decreases gradually. So, you can see that early log phase, it has increased for a certain period of time and then it has decreased gradually as the cell concentration has increased. So, this is your X, this is your QO2. Okay. And now, this is where we were talking about the film theories type, right. So, you have the gas liquid interface and the liquid cell interface. So, your OTR is basically the oxygen that is coming out from the gas into the liquid, that is the oxygen transfer rate, and then your OUR is from the liquid, whatever oxygen is being taken away by the cell. Again, the question would be single cells, in a cluster, things will change because this size of this interface will change. Question is this. So, let us say you have a cluster of cells, right. Now, there is this, let us say, a thin layer of interface over, please excuse my drawing, okay, please excuse my drawing. Now, this particular cell requires oxygen. Now, the oxygen which is coming in has to pass through the other cells to reach that last cell, right. That is why clusters are not good for your bioreactor, because the cells will die, they cannot get enough oxygen for their survival. And that might lead to production of products that are of not your interest, that is something that you do not want. So, you always try to reduce the cluster. What is the way that you can reduce the cluster? Agitation, right. Not this type of agitation, a single one. You have an agitator rotating at a particular speed. Question here, if I may. So, let us say if I give you a bioreactor, I have a sparger that is pumping. I have set the flow rate of oxygen or the flow rate of the gas through the sparger, let us say, okay. Volumetric flow rate would be like, let us say, 50 ml per liter, like 50 ml of oxygen per liter. I am just throwing it in. will the speed of the agitator impact how much oxygen will get dissolved in the water if just the water is here? If I take a dissolved oxygen probe at one end and put it inside of in the fermenter or in the bioreactor, and I change the speed of my agitator, do you think that will change the amount of oxygen that would be present in the water? Because it is going to break the bubbles into smaller bubbles, diffusion changes, smaller bubbles will have smaller interface layer, thinner, not smaller, thinner interface layer. So, your mass transfer is higher. Larger the surface area, more the catalysis, we call it, more smaller the bubbles, is much better it is. The easiest example to that would be the taps that you see these days. The old taps were like just the liquid coming out. These current time, the taps, it gives you that sound, shh, and it comes out in like bubbles, like in streamlines, right? It's less water, but it's very streamlined. So that's why it reduces the amount of water that you're using. Same way, if you streamline, if you basically break all the bubbles into very small bubbles, it will diffuse very easily in the medium. So agitation does impact the OTR, oxygen transfer rate. It's a very important parameter in that case. And that's why when you're trying to think about scale up from a small scale to a larger scale, you have to maintain that OTR. Depending upon, because larger the fermenter, more the OUR. So you have to increase your OTR. So what all you have to increase? You have to increase your agitation system also. And the amount of flow of oxygen, the sparger design, everything will change. That's why scale up is not an easy process. When we're looking at the fermentation, we think about it's a small bottle, I can go to a bigger bottle. It does not replicate just by comparing, okay, in this small bottle I have 2 liters. For 2 liters I used this much of oxygen, so how much will I use for 4 liters? You don't do that calculation anymore. Because if you do that, your OTR is less. You have to now think about what are the other parameters that were impacting my whole thing. Now the viscosity will change, the density will change, because I'm going into bigger system. You have to take into account all the other parameters to estimate the scale up. That's why understanding mass transfer is very, very important before you understand scale up. Any questions? No? Excuse me. Now, if the QO, which is your specific oxygen uptake rate, is the oxygen, if the QO is the oxygen uptake, now small QO is your specific oxygen uptake rate. If the QO is oxygen uptake rate per volume of the broth and QO is your specific oxygen uptake rate, the equation is your QO divided by X. It has to be with respect to the X to give you your specific oxygen uptake rate. So total of oxygen uptake rate divided by per unit volume divided by the cell biomass. So inherent demand of oxygen depends primarily on the biochemical nature of the cell and its nutritional environment. Now, this is also another parameter that has to be taken into account when you are trying to design a particular bioprocess. What it means is that many a times when you are designing a bioprocess, the type of sources you use as your medium source or the nutrient source, how is the bacteria going to utilize it? It's like how much water you're going to drink if you're eating something very, very spicy. It will change the amount of water intake for you depending on the type of food that you're eating, right? Same thing happens with the cells. There's not much of a difference in that sort of concept, but the cell's biochemical pathway will change, and the amount of water demand or oxygen demand will also change depending upon the type of carbon source that they are working with. The other aspect would be the environment. Depending on the temperature outside, the temperature of the medium, the cell metabolism might reduce, the cell metabolism might increase, right? Because if the temperature is at its optimum, the cell growth was optimum. The moment we cross that optimum temperature threshold, you remember from yesterday's lecture, the moment we cross this optimum temperature threshold, the cell starts to die. But it will keep on increasing as I am increasing the temperature. So that means more and more metabolism is taking place, more and more cell mass is growing, my oxygen demand is higher. So the surrounding environmental parameters also impact the amount of oxygen that would be required for the cell to grow. You have to take that into account when you are trying to design your bioreactor again. As the level of dissolved oxygen in the broth falls below a certain point, which is your critical oxygen level, the specific rate of oxygen uptake is also dependent on the oxygen concentration in the broth. So you have to make sure that you have provided enough oxygen beyond the threshold, not less than the threshold, beyond the threshold at all times, to maintain enough oxygen in the broth. The broth that we keep on talking about is the medium. You need to maintain enough oxygen in the broth for the cells to grow. It's the same concept again and again. You have to maintain the oxygen, you have to maintain the oxygen. But that maintenance of oxygen depends on the broth parameters, like the type of sugar that you are taking, the species, the cell species that you have inside, the what else? The properties of the fluid that you are using. So to eliminate dissolved oxygen, just give me 1 second. Oh yeah. So to eliminate dissolved oxygen limitations and allow cell metabolism to function at its optimum, the dissolved oxygen concentration at every point in the fermenter must be above the C critical. So you don't want to be below the C critical at any given point as the fermenter is running. Estimation of the C critical is very, very important. How will you estimate this C critical? Just give me an idea on that. How will you estimate the C critical value? Through experimentation. You will try to see the optimum growth, right? You never go to the fermenter directly, you always go to the seed culture, you have a small scale fermentation unit first, that is what you are trying to optimize first, and then only then you go into the industrial scale fermenter. So you try everything there, understanding the relationship between all the process parameters with your cell growth, and only then you replicate that in a large scale fermenter. You can estimate through that, through experimentation. That's the only way you can do it. The exact value of C critical depends on the organism, but under average conditions, operating conditions, usually falls between 5 to 10% of air saturation. So other way to circumvent the C critical is pump as much as you can. Just pump as much as you can. But that is going to add to the cost. That's why understanding the C critical is important, because when you are working with precision fermentation, you are always giving every parameter at the precise value, at the specific value, nothing more, nothing less. You are trying to optimize your productivity, right? Improve your productivity with the least amount of resources. Oxygen is not a cheap substrate that is added to your fermentation system. So you have to be very careful in estimating the C critical. For cells with relatively high C critical level, the task of transferring sufficient oxygen to maintain the concentration on the liquid side, the CAL, greater than the C critical. Now what is this C critical? C critical is the concentration of oxygen that should be there available for the cells to take, right? So that means I am not bothered about how much oxygen is there in the bubble. I am more bothered about how much oxygen is dissolved in the liquid medium at all times. So, when you are putting your dissolved oxygen probe, you are estimating how much oxygen is dissolved in the medium. That gives you the idea. So, you are trying to maintain that CAL, that means the concentration in the liquid medium, over the C critical value. And it is always more challenging than for the cultures with a low C critical. So, for cells with relatively high C critical level, the task of transferring sufficient oxygen to maintain CAL is always more challenging than for cultures with low CAL or C critical. Why? If I have cells which have a very high OUR, oxygen uptake rate, or the demand is pretty high, you have to maintain a pretty high concentration of CAL, right? Why it is a challenging thing? Fluid properties, like how much oxygen can you dissolve? There is a limitation to it, right? You cannot increase the temperature, you cannot change the pressure. What do you change? You change your agitation, you change how much oxygen you are pumping in. Those are the very few parameters that you can actually handle and control. You cannot play with the temperature and pressure that much, because the moment you change the temperature, you are going to change the growth rate. You don't want to go into the thermal death rate for your microbes, right? You want to maintain it below that. But there are only few parameters that are manageable or can be maintained by you. So, choosing the right host, which will require less and less oxygen and still give you your product, might be an ideal choice to reduce the overall cost of production. If you are choosing something which is of higher oxygen demand, you have to provide more oxygen at all times, and that is going to increase your production cost. So, a lot of parameters gets affected by this. The choice of substrate for the fermentation can also significantly affect your oxygen demand. As glucose is generally consumed more rapidly than other sugars or carbon containing substrates, rate of oxygen demands are higher when glucose is used. Now, you see the relationship between the substrate and the oxygen demand. I am hungry, or I get to see gulab jamun. I love gulab jamun. I will eat a lot of it, but I need to drink water too. It all depends on your choices, right? When they are basically consuming glucose, that means your metabolic pathway is consuming glucose continuously. It is going to need, because cells don't say to themselves, you know what, my tummy is full, I'm going to sit now. I don't want that extra glucose right now. I'm good. No, they will continue dividing. They will continue consuming it. They don't stop like us. They continue consuming it. That creates the situation in which your oxygen is being continuously utilized for the growth of your microbes. So, for that you have to maintain it depending on the choice of the substrate that you have used. You might want to change glucose to galactose or fructose, something which the microbes might not like that much, or the demand of oxygen for the processing of that sugar would be less. So, you have to choose the right carbon source for the growth of your microbes. Now, the step of transport for the gas of oxygen from the gas bubble to the cell, I have already discussed this a little bit. Let's look at it. So, let's say this is your gas bubble inside. This is your gas liquid interface. So, at the gas liquid interface, I said that this is an imaginary or line or imaginary thickness or layer which is present, and that oxygen has to cross through this layer, and only then it will reach the cells. So, oxygen molecules must overcome a series of transport resistances before being utilized by the cell. What about this cell or the cell here? It might get the oxygen from the other sides, but I am just saying that there are other cells around here. It is a cluster. It has to go through now other barriers. So, you will keep on increasing the resistance for the oxygen transport. You are going to reduce the amount of oxygen that is going to be transported. The stagnant medium or the stagnant region is the stagnant the film that we have talked about, the two films on the liquid side and on the gas side. You should have heard about this in certain biomaterials, porous biomaterials which are used to immobilize cell for cell growth, or they can be used for as a scaffold for the cells to grow properly, and they are porous in nature for the nutrients to get transported, for the oxygen to get transported quite easily to the microbes. Those are also utilized these days in the fermentation process to improve the amount of oxygen that is transported into the system. It's like it's a very porous media, and the cells are growing on the surface of these pores or on the surface, and then because it's hollow and porous, the liquid medium with the nutrient and the oxygen can go through. The distance that they have to now move for the oxygen transport is less. So that reduces the amount of resistance. It's like, imagine this as a pen, this as a hollow cylinder, but it's a very small section of it. So there is a small hole in the center, okay? And this whole structure, the cylinder part, is porous in nature. The cells will be growing or immobilized on the surface. Am I correct? Now the nutrient can flow through the hole in the center, on the like axially, and the transport of nutrients can happen through the pores inside. So it's a porous media, the cells are growing on the surface. That is sometimes used for cell culture. Basically, we use that for cell culture. But those type of materials are, or the beads we call them, are generally used in the fermentation system. Even nanomaterials are also being used in the fermentation system. Okay? This is just to improve the overall fermentation efficiency. I want more cell mass, but I want to reduce the overall cost. So if I can do that, why not? Okay, so steps for the oxygen transport from gas bubble to the cell. So transfer through the bulk gas phase in the bubble is relatively fast. The gas liquid interface itself contributes negligible resistance. The gas liquid interface is negligible resistance. The liquid film around is a major resistance for the transport. So you have your gas bubble, it has released the oxygen into the liquid, and then it goes towards the cell. That's the major hindrance or the resistance. In a well mixed fermenter, concentration gradients in the bulk liquid are minimized, and the mass transfer resistance in this region is small. So if you are well mixed, the distance, imagine it this way, the cell cluster is here, the distance of the bubble is not too far, it might be available that the distance, the resistance is less that it has to go through. Single cells are much smaller than the gas bubbles, hence the liquid film surrounding each cell is much thinner than the around the bubbles, and it affects on mass transfer can be neglected completely. If the cells from large clumps, if they form large clumps, liquid film resistance can be significant. Now the other steps for oxygen transport from gas bubble to the cell is resistance at the cell liquid interface is generally neglected. Resistance at the cell liquid interface is generally neglected, not the liquid. So the resistance at the cell and the liquid interface. If this is your cell, the cell and the liquid interface is generally neglected. So when the cells are in clumps, intraparticle resistance is likely to be significant as oxygen has to diffuse through solid pellets like one cell to another cell to reach the interior cells. The magnitude of this resistance depends on the size of the clumps. Larger the size, more the resistance. Smaller the size, less the resistance. Intercellular oxygen transfer resistance is negligible because of small distance involved. We don't consider the resistance at that time when we are trying to estimate the movement of oxygen, because it's not too, like, what is the size of a micro? Microns? So it's not too much of a distance that the oxygen has to get transferred. That's the reason. So, the mass balance for oxygen at a steady state will involve the KLa, that means Cal star minus Cal. The Cal is the concentration at the liquid side, Cal star is on the interface, where your A is A by V, A is your interfacial area, interfacial transfer area, and the V is the broth volume. The KL is your volumetric mass transfer coefficient. This equation above can be used to predict the effect of Cal to changes in the mass transfer operating conditions. For example, if KLa is increased by raising the stirrer speed to reduce the thickness of the boundary layer around the bubbles, the dissolved oxygen concentration, that is Cal, will rise for equilibrium. If you can reduce the film resistance thickness, you will have more Cal, more oxygen in the liquid. Similarly, if the rate of oxygen consumption by the cell accelerates while KLa is unaffected, the Cal will decrease. That means the concentration of oxygen on the liquid side will decrease because now uptake has increased. So, you have to maintain Cal. Whatever you do, maintain Cal at all cost above the C critical. Now, the maximum cell concentration that can be supported by the fermenter oxygen transfer system is an important parameter to look at. So, the way we estimate that is, for a given set of operating conditions, the maximum rate of oxygen transfer occurs when the concentration difference driving force, that is Cl star minus Cal, is highest. So, higher the concentration gradient, more the transfer. That is when the concentration of dissolved Cl is 0. That means, the concentration gradient would be highest when the Cl is 0. Under what condition will the Cl be 0? When your OTR is equal to OUR. So, whatever oxygen comes out from the gas is consumed, comes out, consumed, comes out, consumed. There is no oxygen in the medium. So, your Cal concentration gradient will always be maximum. So, because of that, your mass transfer would be maximum. So, maximum cell concentration can be supported by the mass transfer function of the reactor, and this is the equation that is used. So, your X max, that means the amount of cell, the maximum amount of cell that can be generated. So, if you know the KLa, you know the Cal divided with Q naught, which is your specific oxygen uptake rate. Another important parameter is the minimum KLa required to maintain Cal over C critical in the fermenter. This can be determined as Cla critical is equal to QOX divided by Cl star minus C critical. This is like to maintain the cells that I have right now, what is the minimum Kla value that I have to have? This is the equation that I am trying to use at that time to maintain what I have. Like what is required above, or how much I can get with the respective Kla would be the X max value. If I know what my X max value is and I want to know how much Kla I need to have to maintain that X max, is what I will use the second equation. This is to get what X max I want, I can get. Second is to what Kla I should have to maintain it. Now, determining the mass transfer coefficient, the Kl and A can be calculated using empirical correlations and experimental measurements. Experimental measurements are the most common way of estimating the Kla value. Separate determination of Kl and A is tedious. It is convenient to directly evaluate the product Kla. The combined term Kla is referred as a volumetric mass transfer coefficient. The objective of the fermenter design is to maximize oxygen transfer rate with minimum power consumptions necessary to agitate the fluid and also minimum airflow rate. You got the drift? Least amount of airflow, least amount of agitation, but I still want growth. Right? It sounds like industries. I'll give you least amount of money, but I want the product. Right? And so the boss will come and give you the work, and they'll say, look, okay, I'm not going to give you enough salary, but you have to do it. It's exactly like that. So the reasoning for that is because all of the agitation requires power. Power means energy is consumed. Energy is consumed means what amount of money that is you are going to spend on energy. It becomes an energy intensive process. You don't want it to be. If you're purging in a lot of air inside, you're still spending a lot of money. You don't want that. So you want to reduce the overall cost. So the idea is always you want to design a fermenter, you want to make sure that you are going to use least amount of agitation and the least amount of airflow. So you have to be careful. So what will you do? If I want this, like minimum airflow is required, least amount of agitation is required, what will you do? How will you take care of it? Use the mic.
So whenever we are selecting the media, so the media which having the higher oxygen dissolving property.
So you will select a media that already has oxygen.
No, which have the higher oxygen dissolving property, because the viscosity matter.
The higher oxygen dissolving property. That means it is able to dissolve enough oxygen in it.
Yes.
Okay, got the idea.
But
What media will that be?
it should be less viscous first of all.
It has to be less viscous. Okay.
And
What is the best media that we use in the fermenter system? What do you think is the liquid media that generally we use in the fermenter? Water.
water.
Right? Water is the only one thing that we use. What other parameter can you change?
Well, lower temperature, the dissolution of carbon dioxide is higher, definitely. Hopefully,
Okay.
oxygen also higher. So we can control the metabolism of the organism, which can produce maximum yield at a lower temperature, or we can modify the metabolism according to, genetically modify the organism according to.
Okay. Now, let me put forward a question to you. So, let's say if your intent for your fermenter is to get the maximum cell density and the cell mass. That means you want to grow and grow and grow and grow and grow as much as you can.
Okay.
What will happen to your OUR and OTR?
Even the oxygen uptake will be more than the oxygen transfer rate.
Right?
In
So,
that case.
that means you have to continuously increase your agitation.
Yes, yes.
So, then again it is going to increase your cost. What will you do at that time? But your intent is still to get the maximum yield, but your intent is to use the least amount of agitation. So, you might want to go for a different type of fermentation system, right?
Yes.
Rather than going for, let's say,
Aerobic.
a fed batch or a batch where you have a stirrer. You don't want to use a stirrer. You can go for a fluidized system. In the fluidized system, the cell is mixed because of the movement of the medium itself.
Okay.
And mixing is taking place, you might be able to get more oxygen transfer. There has to be a solution. I'm just trying to throw ideas. I might be wrong in my idea, but I'm just trying to give you some type of solution. You have to find me.
So instead of agitation, we can supply the oxygen as, even for example, sparger, this nozzle can be, the size of the nozzle can be reduced in order to reduce the size of a gas bubbling.
Okay. So that means you want spargers with smaller holes.
Like atomizer.
Okay,
like
atomizers. Very good. that can be used, that is actually used. What else? You have
some
to keep
stabilizers can be used.
stabilizers of for what?
Like even for example in certain industry, for example in ice cream industry and all, they are using certain stabilizer which will stabilize the dissolution of oxygen. But I don't know whether
Come
it's
on,
affect the growth of
you're
microorganisms.
comparing an emulsion with fermentation. And
Not an
a
emulsion.
stabilizer for an emulsion I can understand, because you want to maintain them into their emulsive state, like dispersed state. Yeah.
I don't know whether it's work or this.
No, I really appreciate your effort, that at least you're thinking out of the box. I really appreciate that. But think again, it would be so funny using a stabilizer. What are the most common stabilizers that you use?
Like alginates. And
If you add alginate
yeah,
into
it
your
will
self, what will
thicken.
happen?
Yeah, definitely.
You'll get clumps.
So the media which is used, like whatever the substrate we are used for the fermentation, which also should improve the oxygen dissolution.
See, we are having the same conversation again and again. We are coming back to the media property, more or less. Something has to be done. Neither you are aware of it, neither I am aware of it. It has to be done experimentally. You have to choose, right? You have to go through that whole rigorous experimental process. That's the reason, if you go back to my very first presentation on the fermentation, when I started, I showed you that diagram and I said, like, it has so many pipes. It looks very dangerous. It's a very simple process. Fermentation is a very simple process, but it's very complex. When you go deep into it, it's very, very complex. But once you have optimized it, you come, you switch it on, you forget about it, you go back home. You have your product ready. That's the way it works. For this, yes, there are solutions. The beads I talked about, that's one of the solutions where you might be able to keep your cells suspended without them clumping together. You might give them extra surfaces, so you're increasing the surface area, but you're also helping to improve the nutrient delivery. So you're not going to have like a thick cell mass in which you have, let's say, an agitator the fan blade trying to move. If your cell mass was filamentous, you cannot have an agitation. If you're growing a filamental like a fungi, you cannot have agitation. It will break, right, the filaments. So there are things that can be done. There are a lot of research that keeps on going in the fermentation area. Even if it is the century-old technique, you will still find people doing research in this area just because of this. It is such an interesting area. Okay? Let's get into the final few slides of the oxygen mass transfer. The factors that affect oxygen supply rate, we have already discussed a few of them. Temperature is one of those, pressure is another. Diffusivity. Now the diffusivity of what? Diffusivity of oxygen in the medium or diffusivity in the cell side? It's all about the CLA, right? In the medium, the diffusivity of oxygen in the medium, the viscosity of the medium, density of the medium, surface tension for the air bubbles. Surface tension will define, if I am correct, the thickness of the film. Presence of surfactants. Surfactants can impact oxygen transfer. The ionic strength can impact the oxygen transfer. The concentration of solids can impact oxygen transfer. Power input, less power input, that means less agitation. More power input, higher agitation. Aeration rate. Higher the aeration rate, you will be maintaining more OTR. Geometry of the bioreactor. You will never like to use a bioreactor of this geometry, where only you have a small like impeller in the center and the mass is everywhere else. You are not going to have enough mixing. So, your design of the bioreactor has to be optimized based on mixing. Homogeneity has to be maintained, homogeneous mixing of your nutrients, homogeneous mixing of oxygen, and it should also be capable of maintaining your cell growth. And it ease of operation, ease of cleaning, all of those things come into picture anyway, but your design has to be maintained that way. Now, the variables that can be manipulated majority of the times are your pressure. So, if you increase the pressure, you are basically going to increase your OTR, your shear rate and power input, that means more agitation, you are increasing the OTR. We have already discussed this idea. Aeration velocity will increase your OTR. So, there is a relationship between aeration rate and your agitation rate that can be studied for different mediums. Before I put the cell, if I can study how that will change, then I can provide my cell growth into it. Even that will lead to changes into it, but it will allow me to start with a certain C critical, and then I can increase it depending upon how the cell is growing. I know how much oxygen is required for the cells to grow. I will keep on increasing it depending upon the demand. So, other parameters are for given geometry of the bioreactor depends on the nature of the fermentation process. I will take a break of 15 minutes and then we will start the session on heat transfer operations in the bioreactor. Okay? Welcome back. So, now that we have gone through the mass transfer operations for a bioreactor, we are going to go through the heat transfer operations in a bioreactor. Similar to mass transfer, we did go through the concept of heat transfer at the very beginning of the lecture. So, similar to mass transfer, heat transfers is also a very important parameter when you are looking at the cell growth. We have already discussed about this a little bit in detail yesterday when we were talking about the thermal death or the growth of microbes or how the cell growth is related to the temperature. So, if you increase the temperature, the cell growth will increase to a level which is your optimum temperature value, and below this particular temperature value the cell growth will reduce or they will die. But heat transfer application is not just for the cell growth. In terms of application of heat transfer in let us say in molecular biology or cellular biology, what do you use heat transfer or heat for? Autoclaving, like sterilization. So, anytime you are working with microbes, let us say in any utensil, if whether it is be a fermenter, a batch fermenter or fed batch fermenter or CSTR, or even if you are let us say curdling milk, any container, if you have to clean it, you will be applying heat to kill the microbes. So, that is part of the heat transfer or heat application. In case of fermentation system, we need to have a sterile medium. It should be free of any other microbe, but not free of sucrose or the nutrients that it has to have, but it has to be free of any microbe. So, what do? When you are growing, let's say microbes on an agar plate, what is the very first thing that you do with your agar gel? The agar. You autoclave it, heat it, and then you pour, you let it set, then you streak your organism into it, you see all the growth and everything, and then when you have to get rid of it, autoclave again, right? So, in situ batch sterilization of liquid medium is one of the applications of heat transfer in bioreaction or in bioreactor in fermentation. So, in this process, the fermenter vessel containing medium is heated using steam and held at sterilization temperature for a period of time. It is just like pasteurization. Cooling water is then used to bring the temperature back to normal operating conditions. So, you put in everything, you use the steam to heat the up to the sterilization temperature, you bring it back to an optimum temperature that would be appropriate for your cells to grow. That is when you add your seed culture into it and then you let it ferment. Okay? So, temperature control during reactor operation is very, very important to manage a few things. That would be the metabolic activity of the cells generate heat, because we have to have a temperature control, because as the cells are growing, they are also going to generate heat. The metabolic activity within the cell is generating heat. We have already had this discussion at the very beginning of the lecture today or the session today. So, some microorganisms need extreme temperature conditions. Example would be psychrophilic, thermophilic microorganisms. For those we have to maintain a very high temperature. Now, when you are maintaining these type of organisms, how will you work with your oxygen transport? That will also change. Depending on the temperature of the medium, the oxygen transport rates will also change. So, depending on the organism, we are looking at the OTR. So, you study the organism, you find out what OTR they require, and only then you build the rest of the system on that. But the generation of heat because of the metabolic or the microbial biochemical pathways is an important parameter that you have to take into account. Understanding what microbes you are going to use for your process, how they grow and how much heat do they produce is an important parameter. Now, the heat transfer configuration for bioreactors include jacketed vessels, external coils, internal coils, and external heat exchangers. So, you will have like a jacket around the vessel that will add the heat to the vessel, or you can have external coil into it, and then you have your internal coils which are inside, not on the outside of the fermentation system, but on the inside of the fermentation system. Have you seen a fermenter? I think in today's in the afternoon you are going to see a bioreactor in the lab. Not today? Oh, we don't have the lab today. Okay, sorry. If you do get an opportunity, go to the biotechnology department here. You should be able to see a bioreactor. If you have had a course in bioprocessing, if you have had a lab in that, you should have seen a bioreactor. So, if you are using a glass bioreactor, the only way you can provide the temperature is by using a jacket around it, and then that particular jacket has heating elements into it, and then you pass on the heat to the fermentation system. So, you only jacket it to the level that you put in your fluid, so that you are not providing excessive heat just to the fluid that is of your interest. And then you have your external heat exchanger. I always like these external heat exchangers. They remind me of the old way of heating your water in the morning of winter. You switch on and there is a probe that you put in the bucket, and then you let the water heat, take it out. But that can also be used to murder people. So, don't use that. Anyways, so external heat exchangers are also used to maintain the temperature within a fermentation system. So, heat exchanger configurations. So, I will go with each and every one of them. So, external jackets and coil give low heat transfer area. They are rarely used at industrial scale. They are widely used at lab scale, depending upon how much money you have spent on buying your bioreactor or how much money you have for your bioreactor. In my research group, we have this jacket ones to heat our fermentation system. Then you have your internal coils, which are frequently used in the production vessels. The coils give relatively large heat transfer area because you need more surface area for the transfer of the heat. The coil interfere with the mixing in the vessel and make cleaning of the reactor difficult. So, if you have internal coils, because they are inside it, everything is going to go over the coil. Have you heard about the term fouling, right, or plaque generation over the surface? So, if the heating elements are not cleaned properly, or the fermenter is not cleaned properly, heat exchange would be impacted. So, design of the heat exchanger, where you have the cross flow, parallel flow heat exchangers, when we go into those type of design, even there you have to take into account the fouling process, right. The other would be the coil interferes, another problem is the growth of cells as film on the heat transfer surfaces. Again, fouling. So, those biofilms that get generated on the heat transfer surfaces. So, you have to make sure that you clean these heat transfer surfaces, to maintain an appropriate heat transfer level. External heat exchanger unit is independent of the reactor, easy to scale up, and provides the best heat transfer capability. Sterility must be maintained. The cells must be able to withstand the shear forces imposed during pumping. During aerobic fermentation, the residence time in the heat exchanger must be small enough to ensure that the medium does not become depleted of oxygen. If you are using an external heat exchanger, you want to make sure that the medium does not get depleted of oxygen if you are passing the heat from another source. Sterility has to be maintained, because sterility is the most important parameter in a fermentation process. Because if it was internal, I know everything is inside. Whatever is there inside is what I am working with. If I am using something from another location, I have to make sure the sterility is maintained. Let's say even if I am using some sort of like steam to heat my system, if the steam is being produced at different location and the steam is going to be passed through the pipes, right. When it is going to be passed through the pipes, those pipes have to be clean enough that they don't contain anything. The steam, before it enters in my fermentation system, I have to check that is free of any microbes, right. So, all that controls have to be in place if you are working with an external heat exchanger. Excuse me. So, common heat transfer operations, removing heat generated during the fermentation process. So, the operations that are involved in the fermentation process would be removing the heat generated during fermentation, removing heat generated due to mixing. Almost 90% of the time, the heat generated due to mixing is higher than the heat of reaction. Now, this heat of reaction is not with respect to the chemical reactors. I am talking about this heat of reaction from the microbes perspective, how much energy is being produced by the microbes during the growth. Okay. So, that heat is less compared to the heat generated by mixing. Sterilization operation is a major heat transfer operation in a fermentation system. Sterilization is a major heat transfer operation in a fermenter system. Coming back to this, what sort of mode of heat transfer is this? Is it convection, or we are looking at convection, but we are looking at mostly heat exchangers? If it is internal coils, we are looking at heat exchangers. It's like a heat exchanger. The heat transfer, the LMTD has to be included. You remember that? So you have to take that into account. If it is just from the outside surface and the heat is being provided by the surface of the fermenter, it would be conduction. But if the fluid is moving over the surface, it's conduction at the interface, but there is a flow of the fluid, so convection has to be taken into account. Then again, it will depend on the fluid properties, the viscosity. You have to take you have to look into the table, get the values at a specific temperature. What's the viscosity of the medium, the density of the medium, and then you are going to use your Nusselt's number equations to estimate the value. So microbial growth involves complex network for metabolic reactions. Now I am talking about the heat generation because of the microbes. So during cell growth, cell derive energy from catabolic reaction and use them to drive anabolic reactions. Some energy is lost to the surrounding as heat. If the bioreactor temperature is to be maintained, then this heat must be removed. Hence, the first objective is to quantify the heat released due to the growth. So when you are going into designing a bioreactor, if you have your growth of microbes being, if you're estimating the growth rate, you can also estimate the amount of heat that would be generated by that particular microbes. Once you estimate that value, it becomes easier for you to identify what sources will you choose to remove that heat from the fermentation system. This part is mostly numerical. There are equations that are available to you to do that. I'll give you some of the examples, like what would be the heat of combustion for a biomass, like kilojoules per kg. If you're looking at an E. coli, you're looking at 23.03 kilojoules per gram. For Candida lipolytica, you're looking at 21.34. So depending upon different biomasses, you're going to have different heat of combustions. Once you know your heat of combustions, if you do your in minus out plus generation is equal to accumulation, where will this particular value go? The heat generated by the microbes, will that be an in, or will that be considered as a generation? In would be anything that you are providing, out is whatever you are taking away. Generation can be from the microbes. That will lead to the change in the temperature with respect to time. So when you do that particular balance, you can take into account all the heat sources which are going to add to the system. Now because its generation is adding to the system is positive, if it was removal of the heat, there would have been a negative value, right? That's how simple it is. Now the model equation for the batch system for heat transfer, if you remember, Q is minus Ka dt by dx. Now dx is the distance, dt is the time, or sorry, dt is the temperature difference, dx is the distance. You have to have that gradient. Minus k is your conductivity, sorry, k is your conductivity, is your cross sectional area. But here you are going to look at the QR value with respect to the microbial growth. So this is the equation which is used with respect to microbial growth. This QR is for the microbial growth. VL is the volume, okay, change in biomass concentration with respect to time. dx by dt is your biomass concentration with respect to time. So, I take that into account, the yield, you will be able to estimate how much would be the heat of combustion coming out. So, if you know the heat of combustion, you know the biomass concentration, you can estimate the amount of heat that is coming out for that particular biomass in a given period of time. So, the total heat that has to be removed would be this QR, the heat of combustion or the heat generated by the biomass, and the heat added by mixing. So, Q mixing is the heat generated due to agitation, where we are converting the mechanical energy to the heat energy. Assuming no heat loss to the surrounding, this amount of heat must be removed from the system to maintain constant temperature in the bioreactor. So, if you have a bioreactor, this agitation as it is going around, it is going to generate heat because of the shear stress, right? There is a friction as it is moving through. That heat which is generated, my major concerns, this is my own personal opinion to this, my major concern with respect to the agitation has been that it does not generate a very huge amount of heat. Even if you keep on rotating your hand inside the water, you won't be generating a lot of heat. Yes, you will warm it up a little bit, maybe by a degree or two, but even that small degree or two can impact your fermentation process, because it's a very controlled, precise system. So, heat transfer area should be designed accordingly. So, what you are looking for from the Q mixing is the UA delta T. U is your overall heat transfer coefficient, A is your surface area, delta T is the temperature difference. So, the heat accumulation now would be the heat generation minus the heat removed. So, your dT by dt is the term with respect to your accumulation, the Cp is your heat capacity, density and the volume. Then you are looking at the Q and you are looking at the UA delta T. The QR is your for the biomass, you have it for your mixing, you add both of them, you get the value for the total amount of heat that is going to be generated, that needs to be removed. How do you remove heat in a fermentation system? If you are using the internal coil, those are not heated coils. Let us say those coils are hollow tubes and you are passing steam through them. If you pass cold water, you are going to reduce the temperature, right. If you have a jacket, you pass cold water, you are going to reduce the temperature. So, you always use a medium that is able to extract the heat from the medium of the fermentation medium fairly quickly, because you do not want to have spend too much time in that, right. Longer the medium will remain at a higher temperature, it might lose its viability. So, you want to reduce the amount of time that is required for the removal of the heat and reach the optimum temperature that is required for your cells to grow. That balance is very, very important. Okay? Is there any other idea that you can actually use for removal of heat? You have your
Can use some condensation column, like even circulate it. The circulation can be done.
We
like
did
the
that.
media can be circulated.
Or the
through it.
media can be. So, you are taking the media out of the fermentation system?
No, like even there is a, for example, in pools and all, there is a water purification. The same way, will be like one time it's circulating. Like there is a pipe should be there from the side and is circulating like.
See, you are forgetting two things. So, yes, there is a heat which is being generated by the cell, right?
Yes.
There is a heat which is generated by the mixing. Now, from where are you actually taking away from this heat? From the surface, right?
Yes.
You are not taking the heat from inside the broth or the medium. You are taking the heat away from the surface, from this surface. So, if you increase the surface area, you are able to remove more heat. That is one way of doing it, by increasing the surface area. So, baffles sometimes are not only used to get rid of the eddies, but they are also used to increase the overall heat transfer surface area. Question for you in this case, this is just from the conceptual perspective. So, you have your medium. So, heat is going to pass from your medium to your surface, right? That is conduction. So, do you remember the unsteady state heat transfer? In an unsteady state heat transfer, we have something called as Heisler charts. Heisler charts, you don't remember that? For different types of geometries, if you have like a slab, you have a cylinder or a hollow fiber or a sphere, you can use these charts to estimate what would be the heat transfer, specifically for cylinder, slab and sphere, not for the hollow fibers. I haven't seen that one, but cylinder, slab, sphere, you can use this Heisler chart. But the condition for those Heisler chart was the surface, the condition at the surface, the bound at the surface is maintained throughout the process. It is not changing, but here the things are changing. So, that what it means is, like, let us say if this is a slab, we will always look at the symmetry, and then if this is your x is equal to 0, this becomes your x is equal to L, the length of least resistance, right? So, length of least resistance, that the least amount of distance that the heat has to travel to get out. So, if you are looking at a burger, let us say a burger patty, the aloo patty or potato patty that you get, the heat transfer, if you are doing conduction, what would be the L value in this case? It would be the thickness, not the length, because this is the least resistance. The heat is going to transfer this way. Why I am bringing this is, I am trying to imagine in our conversation with each other, the medium in a cylindrical fermenter system can be considered as a cylinder of uniform conductivity. It can be considered as a cylinder of a uniform conductivity if it is homogeneously mixed. If it is homogeneously mixed, can I consider it to be a uniformly distributed conductive material, a cylindrical? Now, the heat is going from inside to outside if the heat is being removed from the surface, right? Heat is going from inside to outside. Now, as you increase the size of the fermenter, you are increasing the surface area, right? As in a cylinder, like in a slab, the heat transfer is linear. In a cylinder, the heat transfer is not linear, it is parabolic because of an increase in the area, in the radius. So, the surface area keeps on increasing, the heat transfer, the Q will keep on increasing. In this case, how will that impact? If I consider that removal of the heat from the surface, do you think that will have any impact if the material is stationary and if the material is moving? Homogeneous nature is maintained. I have my material heated at a specific value, I have to remove the heat. So, then it becomes, if I am passing cold water on the surface of the jacket, I am basically doing convection, convective heat transfer removal, right, but that would be from a cylindrical surface. It would, will it be considered as a forced convection over a cylindrical surface? There is an equation for forced convection over a cylindrical surface, right, which can be used, that Nusselt number equations. So, those Nusselt number equations can be used if you have a defined geometry of your bioreactor. when you're trying to cool it down, heat it up, you're using those defined Nusselt number equations to estimate the amount of heat transfer.
Yes, we can.
You're getting my idea or the drift? Because I'm considering the whole bioreactor, only the medium part, as a cylinder of homogeneous constant conductivity. There is water flowing over the surface, that means through convection the water jacket is flowing. So, will that be considered as a convective heat transfer? That is what my question is. Will that be considered as a convective heat transfer, or will that be considered as a heat exchanger, or will you consider it to be like a conduction, a basic conduction? Because water is flowing, so convection is there. How will you take it? How will you take it? Like, can you take it as convection? Can you take it as basic?
So convection within the media, and then from the film which is at the boundary layer, from there to the like jacket as conduction.
No, if the medium is moving, then convection.
Yeah.
Right. I'm considering the medium as stationary. It's like a solid cylinder of uniform conductivity because of the homogeneity being maintained. Can I consider the heat that is coming out of that medium, because I'm trying to remove it from the surface, and if I'm passing the water in tubes, will that be considered as a convection, or will that be considered as a heat exchanger?
As a heat exchanger.
As a heat exchanger. So, we generally end up using heat exchanger equations to solve the amount of heat that is being removed from the fermentation system, but we use convective equations to estimate the amount of heat that we are generating within the fermentation system. Okay? So, do not get confused in those two. Now, design equation for a continuous system. So, the heat accumulation is equal to the heat input due to flow, heat out due to flow, heat generated, and the heat removed by cooling. So, your accumulation is this term. So, you have your VL rho Cp dt by dt. You know what is VL? Why VL rho? Volumetric flow rate, or the MCP delta T. V is, what is mass? Volume into density, right? So, you have your volume into density Cp delta T. So, MCP delta T is the amount of heat which is there accumulated within the system. Clear? So, this term is your MCP delta T. Similarly, break it down for yourself. First thing is heat input due to flow. F is your flow, rho Cp. Now, this becomes volumetric flow. F is your volumetric flow. So, that becomes your mass flow rate. This is your heat generated because of biomass. This is the heat added because of mixing. This is the heat being removed. This Tc is the cold temperature, right? This is the heat being removed. UA delta T, U is your overall heat transfer coefficient, but we are looking at it as from conduction perspective or convective perspective. Convection, UA delta T, okay? We are looking from the convection perspective. So, understand, like MCP delta T is the key here. So, do not get confused by the overall these big equations. MCP delta T is what the VL rho Cp is. The volume into density will give you the mass, the Cp, then the delta T. So, model equation should be able to predict what heat transfer area is needed to achieve the required temperature time profile. So, if you are able to identify these equations, once you solve these equations, you will be able to predict what heat transfer area is required or is needed to achieve the required temperature time profile. Okay? So, if you are designing your bioreactor, if you know how much heat is being generated by the biomass, what would be the removal of the heat, you can design inside again the area. So, you can add baffles just in case if you want to improve the overall removal of heat, you can add baffles. If you do not need, you can change the number of coils that you will have. So, you can do a lot of those modifications to your design of the bioreactor depending upon what heat requirement is or what heat removal requirement is. Then comes the topic of scale up. Okay? So, mass transfer done. Heat transfer is mostly for sterilization purposes. Heat transfer application is mostly for sterilization purposes. I am not going to teach you the log 10 reductions. Okay? That is not part of this, or it is not in the scope of our conversation today. You can check when you are working on the sterilization pasteurization purposes for your own courses. The idea of heat transfer in the fermentation system is because of the sterilization of the media, because everything has to be sterile to start with. Once you add your culture to it or the seed culture to it, that is when it will start growing. The other aspect of the heat transfer was to maintain the heat for the optimal growth of your microbes. That is by your mixing the heat that is being added, the generation of the biomass, the heat that is being added, and how much you can remove UA delta T, right. So, that was what was involved. Now, look at the scale up. Now, you have understood your mass transfer and the heat transfer. Now, keep those concepts in mind and then think about your scale up. All of those parameters have to be transferred if you are moving from a small fermenter to a larger fermenter. Your OTR, OUR has to be maintained. Your removal of heat has to be maintained. The agitation speed that you were using in a smaller fermenter might not be the same as a larger fermenter. The amount of power input for that agitation will differ if you are working on a larger fermenter. So, all of that power ratio has to be maintained when you are looking at scale up. So, what is the scale up in practice? Scale up, it is the study of problems associated with the transfer of experimental data from laboratories and pilot plants equipments to a large scale industrial equipment. So, you are starting from a test tube to a 5 ml flask, 35 ml flask to 200 ml flasks. Then you go to a 5 liter bioreactor, move to a 30 liter bioreactor, 220 liter bioreactor. I personally have seen up to 1000 liter bioreactors. Then you go to 10,000 liter bioreactors. We have already scaled up these bioreactors up to 600,000 liters now. There are bioreactors of capabilities of 600,000 liters. Think about it. Now, it's a very scaling, it's a process that can be scaled up quickly, but it has to be done in a proper way, because there are so many parameters that depends on the scale up process itself. Your heat transfer, mass transfer specifically your oxygen. Whenever you think about mass transfer in a fermentation system, it's all about oxygen. When you think about heat transfer in fermentation system, the heat generated by the biomass plus the stirring is not that significant. It's all about sterilization. The most important part will be the sterilization. That's the most important heat transfer application in the fermentation process. What else will you take into account if you are thinking about the scale up? The geometry of your bioreactor, that has to be taken into account, right? The diameter, the height, all of that has to be taken into account. The third most important, the nature of your organism has to be taken into account. The fourth, so nature of the organism, heat, and mass. What else was there? This agitation is going to impact mass, is going to impact heat. What else? Aeration. Agitation is going to impact aeration, aeration is going to impact mass, aeration is also going to impact heat. Can I? No. No. Aeration is mostly for the mass transfer applications, okay? What else will you take into account when you are looking at scale up? You have taken your bioprocess course, come on. Thinky. I can see people's mouth moving, but I cannot hear anything, honestly. Give it a try, there is no wrong answer. Let her answer first.
Just 3 parameters we mainly consider about. One is KLA.
Okay, that is your aeration, mass transfer.
Yeah, so and impeller tip speed.
Tip speed, that is your agitation.
Yes, sir. You've written everything, sir.
Then what else is there?
What
And the
else?
geometry, right?
Yeah,
These are
yes,
the
the
three that
geometry.
will take care.
Power, sir. Power consumption.
Power consumption is also agitation.
Yes, sir. PYV.
Yeah, but then it is used for what? Power is used for what?
Again comes to the aeration agitation. But these are the 3 things mainly, but you've written already, sir.
Yes, but I am seeing it from a different perspective, right? As a faculty, my intent is that you don't give me the bookish example of the tip speed and all those things. You give me from the conceptual, whatever you have understood it till now. We have discussed batch reactors, we have discussed fed batch reactor, we have discussed how to design a batch reactor, we have discussed how to design a fed batch reactor. You know, none of you have talked to me about when you are changing the geometry, you are also going to change the flow of your feed. Your feed rates will change. There are so many parameters change the moment you change the design of your bioreactor, or even when you scale it up. There are a lot of things that come into picture. The most important that are used to take, if I have to take this pen, make a bigger pen, I will take the things that I can control. The first thing is the geometry that I can actually control and pass it on. That's why you were talking about that. Now, tip speed and all those things affect your agitation, affect your KLA values. How many, let's say, for a small fermenter, for a small fermenter, can use only one impeller. But what was the design of the impeller that I was using for a small fermenter might not work if I move it to a bigger fermenter. What will you do then? The agitation will change, right? So it requires some consistency, but there are also certain parameters where variability exists. That variability is what matters the most. But fermentation is a very forgiving unit operation. That's why I said it's a very simple system. It's like one of the nicest unit operation that you can work with. It's also very forgiving. You add everything, you will get something at least. But if you are able to put a little bit of effort in understanding each and every intricacies and then design it, it will give you the best of it. That's what the intent is in our conversation. I can understand what you told me, the tip speed. I have all of that in my slides next. But I just wanted to get a bit more from you. What else will you change if you are moving from one smaller fermenter to a larger fermenter? What else will you change? Are we just focusing on the batch? If we are only focusing on the batch, I will not care about the feed. Will I care about the feed? I won't. What if I am trying to scale up on a fed batch level? I have to think about my feed rates, my flow rates. So that has to be scaled up depending upon how much I want to grow. But that would also come with a different set of calculation, but that has nothing to do with the design of the fermenter. You're getting my point? That has to do with my working. but it has nothing to do with my design of the fermenter. That's the reason why feeds and all those things are not taken into account. That will only depend on the growth productivity that you want. Productivity has nothing to do with respect to the design in terms of, like in our conversation I'm just saying. It's just physical conversion of a small thing into a bigger thing. That is what we are talking about. So, we will get more into this. So, what is the exact aim of scaling up? The objective is to keep the cellular environment constant. Your cellular environment has to be constant across scales to achieve comparable growth. I am not using the term exact. I wish I can use the term exact, but I am using a comparable. You might not get an exact growth, but you will get a comparable growth, relatively comparable growth, metabolism, productivity and product quality. Sometimes, like people make fun of these things where they will say it's like a one-time wonder, right? Your thing worked at the lab scale, the moment you scaled it up, it didn't. There is something wrong in the input for your large scale. That's what the problem is. There is nothing wrong at a small scale, but there is something which is missing at the large scale. Understanding that from the biochemical perspective, everything will remain the same. It's mostly the physical that thing has changed. From a small fermenter, I became a bigger fermenter. That's it. I used to be a thin guy, now I'm a big guy. It changes, but inside, I remain the same. I used to be the same person 10 years back, I am the same person 10 years now, or I will be the same person 10 years after, except I would be much more older, but my body will change. That's what the scale up is all about, is you are changing the physical aspect, but internal has to be constant. You're trying to maintain it as much as possible. So, which are the most important criteria, similarity criteria? Now, we talked about that, and thank you for bringing all of that answers. So, similarity criteria that you have to maintain would be your mass transport, which is your O2 and the CO2. The CO2 which is being generated has to be removed. Larger the fermenter, more the biomass, more the CO2, more the removal. Larger the fermenter, more the biomass, more the O2, more is required. Mechanical stress on the cells. Larger the biomass, bigger the agitators and the impellers, the design of the impellers, more the stress, shear stress. Larger the population, too many people, right? It's just like going in an auto rickshaw or you are going in a crowded bus. Scaled up. Stress, right? From the cell's perspective. Mixing time that would have been required at a small scale would be very different than the mixing time that would be required at a larger scale. So, how quickly can you reach the homogeneous or homogeneity is very, very important when you are trying to do scale up. Now, these are the most important parameters from the industrial perspective. Think about, I am so proud that you all are aware of the basics of scale up. I am really, really proud of that. Think it from a completely, I said you keep an open mind. Think it from your own project, your own experiences. How are you going to do the scale up? What are the parameters that will get impacted the most? That has to be taken into account. Oh, sorry. Okay. Yeah. So, the scale up principles involve ensuring circulation of nutrients, dissolved gases and removing metabolites is an important in bioreactor. Agitation and aeration allows for the bulk liquid mixing and shear stress. Agitation adds to that. Oxygen transport and PCO2 removal is through the aeration aspect. Mixing is more difficult as scales increases. Mixing does become an issue as the scale increases. So, on the right hand side you can see the process definitions. I will like you all to look at this particular link to get the same graphs that I am using here. So, temperature control. So, temperature is directly related to cell growth and viability. Okay. Then temperature control also regulates the O2 and the CO2 solubilities. Then you have your pressure control. Pressure control basically impacts your CO2 and O2 solubilities, and that impacts your cellular environment. Nutrient addition, your glucose, glutamine and the feed addition. Nutrient concentration, that will impact your cellular environment. If you are looking at the pH, you have your base addition. Now, why do you add a base? To maintain the pH, right? So, now the base, if the base and the substrate will interact or some other combinations get generated, that is going to impact your cellular environment. The one comes here is the focus, the dissolved oxygen control. So, dissolved oxygen control is through agitation, gas flow rates and the sparger type. The type of sparger that you are going to use. At a small scale, I could have had a ring sparger. At a large scale, what will I do? If I have a larger, like as big as this, if I have a larger sparger here, the bubbles are going only in the corner, nothing is going to come in the center. So, I have to design a sparger which is multi-layered, right? So, you have to think about the design from that perspective. Nobody talks about scaling up of a sparger. People are talking about the scaling up of aeration, the O2, but that will lead to the change in the design of the sparger. So, as an engineer, I understand the O2, that what the biochemical guys or biochemical engineer is interested in the O2. He or she will come and say, well, hey bro, I need this. I say, okay, fine, I have to redesign the sparger. As an engineer, I would love to do that. That's my area of interest. How to redesign the sparger to make sure that you are able to maintain the O2 that you require. Now, if the cellular environment is maintained, that will impact your cell growth viabilities, nutrient uptake and waste accumulation. That will also look into your product concentration and the product quality. Maintaining all of this is your primary motive with respect to scale up. Now, determining the derived parameters in reference to those would be you calculate your agitation regime. So, you have to look at your eddy size, the power density, the tip speed, the mixing time, the KLA and the turbulent shear force. Then you calculate. So, once you have estimated, you again calculate your aeration regime. You have your porosity spargers, airflow spargers, oxygen flow spargers. Then you have another second round of porosity spargers or airflow spargers. You have, if you need more, an agitation aeration regime for a targeted scale determination has to be determined depending upon O2, CO2 removal, mixing time, tip speed. These are the main ones. This is an example. So, if you are scaling up a 1 liter bioreactor to a 100 liter volume based bioreactor, so the volume is pi T1 square by 4. So, T1 is your diameter for the smaller one. So, pi d by 4, right, d square by 4. H1 is your height for a small one. So, you are looking at S. This S is the parameter that we use for scale up, or this is also called a scale up parameter from the geometry perspective. So, you are looking at scale up from the diameters of the spargers, of the impeller. You are looking at the diameter of the vessel. You are also looking at the distance of the impeller, the tip of the impeller and the base. Does that impact the speed of the impeller? The distance at which it is placed? That will impact your mixing. So, a single scale ratio S, this is called your single scale ratio S, defines the relative magnitude of all linear dimensions between the large and the small scale. Okay, so, volume 1 is given as this, volume 2 is for the larger one. If you take a ratio of volume 2 and volume 1, the S value for your case should be 100 to the power 1 by 3. If you make it a 10 liter, let's say, every place where you have 100 will become a 10. So, this will become 10 1 by 3. 10s are easier to work. For 1 you go to 10, 10 to 100, 100, 1000. An increment of 10 makes your life much more easier. Excuse me. Any questions? No question? Now, the scale up strategies, tip speed. So, tip speed is defined as the tangential velocity of an impeller at a point on its tip. The tip speed is a function of the RPM, revolutions per minute, and the diameter of the impeller. So, diameter of the impeller or the size of the impeller will define the tip speed. So, the tip speed is pi dn. The d is your impeller diameter and n is the impeller agitation rate. So, the RPM that you are talking about. The criteria is you ensure the L by D, the length by diameter, to be the same in both cases. So, L by D in a small scale, L by D in the large scale. The agitators should be identical, They might not be identical depending upon how big an agitation system you go to or what type of design you all had before. It does not take into account the impeller design at all. This one does not take into account the impeller design. So, if you have a specific impeller with a twisted hook at one end, you might want to have the same in the other one. Sometimes it is possible, sometimes it is not possible. So, when that happens, you have to redesign your smaller one with a different impeller and then see if that can be used, or you have to compare again. So, you take that twisted one, you still think that it is a flat, and then you use the flat one on the other side and then compare the performance, the productivity. If it is comparable, you are good to go. If it is not comparable, do not go with it. Now, the other scale up strategy involves the power per unit volume, the watt per meter cube. The power per unit volume, sometimes referred to as power density, is the power output for a given volume of culture. So, impeller design, fluid density and the agitation rates are considered in the power per unit volume. So, your NP is the impeller power in number, rho is your fluid density, N3 or n to the power 3, N is your impeller agitation rate, the D is your impeller diameter, the V is the liquid working volume and the P naught is the ungassed power input. This power input is just with respect to aeration or agitation. It is just agitation, okay? There is no aeration yet, it is just agitation. So, larger the fermenter, larger the agitation system that you use, larger the amount of power that you are going to consume. Redesign it, you might be able to make it cheaper. Questions? Now, shall I continue? The other scale up strategy comes for the KLA. So, she was right, you have KLA, tip speed, power density. I am going to put you on place, do not worry about that. So, tip speed, power density, KLA. KLA is for the aeration. Now, tip speed, power density is mostly for the agitation or the design of the geometry. Tip speed is for with respect to geometry also. Power density is with the impeller, the agitation purpose. KLA is with respect to the oxygen mass transfer coefficient. So, this is a parameter that controls the rate of how oxygen transitions from the gas phase into the liquid phase. The intent is sufficient O or air delivery is required to support cell growth, the metabolic pathways or cell metabolism itself, the protein productions requires oxygen. If you are using the host, that requires oxygen. It is also to prevent excessive CO2 in the media, which can impact critical performance endpoints. So, physical KLa are determined by various power by volume ratios you can use, and the gas flow rates, the VBMs, using the static gassing out method. You know what the static gassing out method is? What is it? You have the mic? Wait, somebody give it the mic.
First of all, we supply the gas, then we allow the bacteria to or microbe to utilize the complete amount of gas, and then we sparge again. Then we know how much gas was utilized.
Okay. Now, there are different methods to measure the KLa. One method I remember is you estimate the amount of oxygen that is there at the beginning of the fermenter as you are passing in, and then you measure how much is coming out. So, that will give you the difference of how much oxygen is required. Another one is where you pass in the oxygen, you let the growth, and then you purge the nitrogen to remove all that oxygen, and then you estimate, and then you pass the oxygen again, right? So, that's the static.
Dynamic gassing.
That's the one, right?
Yes.
The static and dynamic one. Okay.
And also there is a sodium sulfite oxidation method.
That I am not aware of. I know about these two. That's what I have read in my undergrad. I have not used them yet, but those are the ones which. Oh no, for the KLa we have used the static one. Anyways, so the KLa is defined as oxygen transfer rate divided by the DO, which is your dissolved oxygen saturation concentration. So, OTR divided by the C star. Biological KLa depends on the clone and maximum viable cell concentration. So, you remember that X value that we have looked at, how we estimate how much biomass we can generate with respect to the oxygen concentration that we have, and if we have a specific biomass concentration, how to estimate how much oxygen we require. We did that back equation, it was also there. So, KLa bio specifically for biological purposes would be your oxygen uptake rate divided by the dissolved oxygen saturation concentration. So, OUR max divided by the C star. The oxygen uptake rate is not known at all times. Sometimes it is not known. What will you do in that case? You run. The system is learned by experience, so it has to estimate it experimentally. That is why fermentation is not successful in the very first go that you go through. It takes time for the fermentation to build up. Once you are set with all the parameters for your fermentation system, you are in the best condition possible. So, to prevent oxygen limitation, available KLa for a bioreactor design should be superior to the biological KLa demand of the cell lines in culture. That means, your OTR should always be higher than your OUR, as simple as that. Your OTR has to be greater than OUR. Clear up to here? Now, what are the difficulties with respect to your scale up? If I am looking from the geometric similarity, large bioreactors are physically different from small ones. They are physically different from the small ones. So, there is nothing else I can talk about in that. They are just physically different. So, sometimes it is not that viable when you are trying to do the scale up. It is not easy. Mixing time, the fluid dynamics vary in large scale bioreactors, causing differences in mixing times due to size and geometry variations. The power input per volume difficult to maintain consistent power input per unit volume due to the equipment constraints and the fluid property differences. It changes, the fluid properties will change depending on the volume. Oxygen mass transfer coefficient, larger bioreactors can have reduced oxygen mass transfer coefficients. Why? Limitation in gas liquid interaction impacting cell growth and product yield. So, finding the appropriate size, it's not like that, hey, I have been successful in this 10 liter bioreactor in my lab, let's go and make 100,000 liter bioreactor. It doesn't work like that. You go from 10 liters, max you go up to 200 liters. You try in that. If it works, perfect. If you can scale that up, then you go for 600 liters. You don't go 100,000 immediately. You have to be very cautious, because as you scale up, the difficulties will increase. So, you only go up to the extent where you know that you are going to get the maximum productivity. Okay? The tip speed, the larger bioreactors require larger impellers, resulting in variations in tip speed compared to small vessels, affecting the shear stress and the cell behavior. It will not mix properly, cell clusters might appear, homogeneity cannot be maintained. So, all of this comes into picture when you are looking at from the difficulty for the scale up purpose. Now, this is an example where you are looking at scale up strategies for, let us say, if you are doing antibodies production or the viral proteins or the cell production. So, if you are looking at antibodies, so production of monoclonal or polyclonal antibodies for therapy, diagnosis or research, you use mammalian cells. Example would be the CHO cells, which are your mammalian cells. The process involves cell growth, antibody expression and purification. The emphasis for this type of fermentation is on the mass transfer for nutrient and oxygen supply. So, that is our core focus when we are looking at mammalian cells. Shear force management to protect fragile antibody producing cells. So, your agitation, you have to be very careful about it, because it might break the cells which are going to produce your antibodies. So, depending upon the type of product you are going to make, your scale up practices will also change. Clear? Or the choice of design of bioreactor will also change. Let us go on the virus side. So, virus production involves the manufacture of viral vectors, which are used in gene therapy to deliver genetic materials into the target cells. Production of viral vectors often using adherent or suspension cell cultures, example is given to you here. The process involves transfection, viral replication and purification steps. Crucial focus is on controlling mass transfer for efficient nutrient supply. Shear force management is essential to preserve the integrity and productivity of the viral vectors. Again, agitation has to be very controlled in this case, but you do need the mass transfer, right. So, agitation has to be there to make sure the mixing is there, mixing exists for the oxygen to get your OTR to be higher than your OUR. Similarly, on the cell side, so cell production for therapies like CAR T cells or the stem cells involves cell expansion and differentiation to generate sufficient numbers of therapeutic cells. If you are looking from the cellular agriculture, if I am looking at stem cells get differentiated into different types of cells. That is where this type of situation will come if you are looking from cellular agriculture. So, during cell production, it is critical to optimize mass transfer for adequate nutrients and oxygen delivery to maintain cell health and function throughout the expansion process. Additionally, managing shear forces is vital to prevent damage to the cultured cells, ensuring they remain viable and functional. So, for almost all of them, O2 agitation is important. So, if you go from small scale to large scale, you have to make sure the O2 and the agitation can be maintained. You maintain the agitation, you maintain your O2. But O2 also involves the sparger, right? It also involves putting in the oxygen in the system. Mixing will allow to better the OTR, right? It will also help for the viable growth of the cells. So, you have to make sure the agitation is proper, so that the mixing takes place. Now, there are also regulatory aspects to bioprocess design. This is the, I think, the last slide for us today. So, the regulatory aspects for the bioprocess design involved are product quality and purity, the sterility assurance, the validation and qualification, and the scale-up validation. These are the three that are the most important. So, what is about the product quality and purity? Consistent bioprocess design is required to achieve rigorous control over the quality and purity of the therapeutic products. The core focus of the fermentation industry is not only on food, but fermentation is also widely utilized for therapeutic drugs. From that perspective, the purity and the quality is primary requirement, okay? Because that is where the regulatory people will come into picture, because the purity and the quality has to be maintained if it is being used for therapeutic purposes, for medicinal purposes. The sterility assurance, maintaining sterility to prevent contamination. You have to maintain sterility to prevent contamination. You cannot expect any contamination anywhere. Traceability, documentation and traceability of each step in the bioprocess for product safety and regulatory compliance. If you are making any changes to the process parameters, those have to be documented, because that will lead to changes to the product quality. If the product quality changes, you have a written documentation to know why. You would be able to trace the reasoning for it, okay? Validation and qualification, validating and qualifying the bioprocess in producing safe and effective therapies consistently. So, whenever you are doing any sort of these bioprocessing, they have to be consistent and you can validate them. Scale-up validation requires the scale-up procedures are validated and meet quality and safety standards. So, it is not like I have one bottle in my room and I go and buy a drum and put everything inside and start doing fermentation in it. You have to take into account the safety regulations, because if you are working with microbes, some of the microbes that you would be working on, let's say if you are doing fermentation, they are recombinantly generated, right. So, they are genetically modified. So, if those microbes, if God forbid, if they are pathogenic in nature, what will happen? Things can go wrong. So, you have to be very careful when you are trying to do the design of these. Siba? Cool. I hope you have learned something with respect to your bioreactor design and analysis till now, with respect to scale up, the batch design, the fed batch design, the mass transfers, the heat transfer. We also had an amazing time discussing about cellular agriculture, the precision fermentation, and not so amazing time thinking about synthetic biology, systems biology, and enzyme engineering. Why I said not so wonderful? Because I felt that I would have given you more information, I should have been more prepared for it, but I felt that that way, that I should have been more prepared. But I hope you enjoyed. Okay? I wish that you can work on your case studies, case study 1 and case study 2, and please try to submit it today in the evening, so that we can assemble all the presentations, and that would be, so we have to assemble it with respect to the case study 1 and the case study 2. When you come tomorrow, you will be presenting all the case study 1 in one of the sessions and all the case study 2 in the other session, and then we will have this type of conversation where we will have back and forth why you chose this particular host, what was the requirement of this particular host, whether this is necessary, that is necessary. We will be looking at all of that. Any questions for me before we end the session today? You all look hungry. So thank you. That will be the end for today's session.